All right, for this lecture we're going to talk a little bit about sampling gear and just a few more details in some of the sampling gear. The first thing I want to talk about is we make this distinction between passive and active gear. And it's pretty much what it sounds like. Passive basically just sits there. There's not much effort, and the fish catches itself. Active gear is what it sounds like. You're putting more effort into it, you're moving around, you're actively trying to catch the fish. And some gears clearly fall into one or the other types, and some maybe it's not always so clear, but that's just something that helps us organize our thinking. So some of the passive methods that we're going to talk about are gill nets, trammel nets, hoop nets, trap nets, which are also called fyke nets, and trot lines. So let's talk about gill and trammel nets. Typically these days they're made of monofilament. If you've gone fishing, it's basically fishing line. And the advantages here are that it's clear, and so it's harder to see, you catch more fish. The disadvantage is that it breaks easier, and that could be bad. Potentially the fish could break free. That also may be good. If you are snagged, for example, you can often tear part of the net and get the whole net back, whereas if it didn't tear, the net would be just stuck down there at the bottom of the lake. Older nets, or some different kinds of nets, are made of nylon. Nylon, just very thin string. And so this is much stronger than monofilament, but it's also much easier to see, and the fish tend to avoid these kind of nets. And so that's why most of your gill nets are made from monofilament. And if we look, zoom in on a net, an important concept here that you have to know is the mesh size. Well, of course you understand that mesh size is important, and mesh size has a huge effect on what kinds of fish you're going to catch. And surprisingly, small changes in mesh size can really affect the distribution of the size of fish that you catch. But you also have to be careful about how you label the mesh size. What I'm showing you here are the two ways that we measure mesh size. One is bar or square mesh. Let me pull up a pointer here. And that is just one side of the diamond, okay? You contrast that with what we call stretch mesh, which are two consecutive sides of the diamond, which you see here and here. And it's called stretch mesh because you grab two opposite knots and you stretch it, and that's what you would record as the mesh size. And so the idea being that stretched mesh is probably a little bit more indicative of what size fish you can catch. It doesn't matter. What matters is that you clearly indicate whether you have, say, for example, a 2-inch bar mesh or a 2-inch stretch mesh. Those are going to be very different sizes. And I personal experience with this, I've ordered the wrong net size before because I indicated stretch mesh when I meant bar mesh, and you get a very different size. So that's what that means. And of course, here's just an example of what a gill net looks like. There are different ways you can fish them. You can fish them at the bottom like you see here. So you notice that this net is sitting along the bottom. You can fish them in the midwater. You can fish them at top. You can drift them, which is to deploy them perpendicular to the current, and then it just drifts with the current. As you can imagine, it gets snagged quite a bit that way. However, you also catch a lot of fish that way. And they're called gill nets because the fish gets gilled or trapped by the opercular cover when it gets in the net. And here's an example of a channel catfish that gets wrapped up in a net. Now these nets can be pretty tough on fish if they're in there a long time. It's tough on their gills, and it's very stressful, and so in warmer water we tend to not fish them very long, and things like that. A trammel net is similar to a gill net, but it's really 3 nets in one. You've got basically 3 gill nets, and they're tied together at the top and the bottom. And the outer two panels are usually nylon, and the inner panel is usually monofilament. And the mesh is much bigger on the outer ones. And what happens is the fish tries to push through, and instead of getting gilled, it gets bagged. It sort of creates a bag that catches the fish. And this is just a different way to fish these nets, and it catches different species sometimes. And you can see here in this example that this is what a trammel net looks like, and you can see how this fish is, it's kind of created a little bag there that's trapped the fish in. A hoop net is just what it sounds like. It's a series of hoops. Again, don't forget that these things have these inverted cones, just called the throat. And this one has two inverted cones in it. And that's the key, is that the fish swims in and swims down the cone, and then it's much less likely to find its way back out. You'll notice how this is being fished with the current. A lot of times the fish will just swim in here looking for a current break, but a lot of times you'll bait the net back here, and the fish will swim in looking for the bait. Trap nets we fished in class. It's just a hoop net with a box on the front. Again, these are also called fyke nets. And you've got this lead on it. And this is what it looks like when they're fished in shallow water. This is really about one of the most effective ways to fish a trap net, with it sticking out of the water a little bit. That greatly improves turtle survival, because you will catch a lot of turtles, and this way the turtles can get up and get a breath. But it's very effective. If you have the banks that are too steep, then the trap net's going to be at too much of an angle, and the fish is going to just swim right over top of it. Now I've got a short video here demonstrating how a trap net works, starring my daughter, Sophia. So the fish swims until it hits the lead, and then it naturally follows the lead to deeper water and right into the net. We got something! What did we get? A Sophie fish! Let's get it out. Get it out of the net. Now the last passive gear we're going to talk about is a trot line, which is basically just a long heavy rope with a series of droppers on it. You can see the droppers here, and at the end of each dropper is a hook. And you bait the hook and deploy this, and it's basically a way to fish multiple hooks at one time. And this is being shown as this one is being fished on the bottom, but you can fish these in mid-water, you can fish these at top. In the marine fisheries, they're called long lines. What I just saw a recent research project, which is kind of cool, where they deployed sensors, and whenever a fish got on the hook, it tripped that sensor, and so the sensor can tell you when the fish was caught. And in fact, this paper showed that most of the fish were caught within the first 15-20 minutes so that we can deploy. So this is something you could probably deploy for a short time and have some success. That's not necessarily true. A lot of times you have to deploy these overnight, because that's when the fish are going to be moving around. But this is an effective gear a lot of times for sturgeon, catfish, and of course recreationally people fish trot lines a lot too. All right. So you can kind of see what we mean by passive methods there, where the gear just kind of sits there and the fish kind of catches itself. We also have many active methods, and we're going to talk about some of these, but not all, but things like trawls, minnow seines, other kinds of seines, push nets, ichthyoplankton tows, spears, poison, dynamite, and then finally electrofishing. We're not going to talk about all of these. When we talk about trawls, The one rule of thumb you have to remember is this magic 7-to-1 ratio. This ratio turns up a lot of times in fisheries, like for the size of a net, often needs to be 7-to-1. Here we're talking about the ratio between the length of the tow ropes and the trawl depths. So roughly those are usually in about a 7-to-1 ratio. So for example, if you want to trawl 3 meters deep, you're going to need ropes that are at least 21 meters long. And here's a trawl, and we've got some different terminology here. The trawl is held open by what they call trawl doors. Around here we call them otter doors. And those contain the ropes that are attached to the boat. And their function is to catch the water and to hold the mouth of the trawl open. And they call this the headline and the foot rope. What we call them is the float line and the lead line. So the lead line's got lead, it drags along the bottom. Sometimes there's a chain for the lead line. And then you've got floats on the float line which help to hold the top up. And as you pull this through, you just scrape along and the fish get caught, and then they work their way back here to the cod end. And again, you can fish these on the bottom, mid-water, or up top. Of course, this is a simple beach seine. We call them minnow seines around here. Fairly straightforward. Drag it through the water. Again, of course, mesh size is very important, as well as the length of the seine and the depth of the seine. And then if you add a bag to it, you seem to have a lot more luck. So you can see here in the middle of this seine that they've got a bag there, and the fish tend to get in the bag and stay in there, and you tend to have much higher catch rates with a bag seine. A purse seine is kind of cool. This is usually this is a much bigger gear. This is something that is fished in the ocean, but I know they've been trying to use this to get Asian carp on the bigger rivers. You see here that you have a float that's deployed, and one end of the seine is tied to it, and then it's actually a boat drives around, so it's a much larger seine. Makes a big circle, the idea being that you circle any schools of fish. And then on the lead line, or the bottom of this, now this is being fished kind of at the surface, the bottom has a line that slips through a series of rings like shower curtain rings, which allows you to pull in that bottom and cinch up that bottom. It's just like the drawstrings on the top of a duffel bag or something like that. And as you pull that bottom string, you just cinch that bottom, and now you've got them all trapped in this bag, and then you can just pull the whole thing in. This is an example of a push net. Pretty straightforward. It's a net that you push. Mounted on the front of the boat. This is often used, they call these for shad, they call these shad scoops sometimes. And it's pretty obvious how this thing works. This is something neat I just found just on the internet one day. Beach push net for collecting small fish along a soft bottom, like a sandy bottom. You see that he's got a couple of different cod ends here. I'm betting that they've got two so that you can get your stand closer to the handle here. You also notice that it's on skis, so it slides along the beach better. Another cool kind of gear that I've seen fished before is something called a pop net. Basically, this is a net that is all collapsed on the bottom, and it has some sort of trigger. And so you collapse the net, and you deploy the trigger, and then you just walk away for a while. And you let everything settle down, and the fish kind of move back in, and then you sneak up and you pull the trigger, and the net pops up and catches all the fish inside. So here we've got this net collapsed on the bottom. Imagine a square made out of PVC pipe, two squares made out of PVC pipe with a net going in between them, and then the top square is pushed down. So here you've got this net all bunched up and you've got something holding that top down and a trigger on a float somewhere nearby. So you deploy this, the fish move back in, and then when you hit the trigger, that top part is released and it shoots to the surface, trapping fish inside the net. And so, for example, I've seen this used when people are trying to study vegetation use by fish. Vegetation is kind of hard to sample, but if you were to build one of these around some vegetation, and then once the fish move back in, you could pop up and catch them. The next active method that I'm going to talk about is electrofishing, which is one of the more common ones. And it works so well because it has the least amount of bias. There's bias to electrofishing, but not as much as, say, with gill nets. Your gill nets are going to be biased against certain size classes. Or something, like a trot line is going to be biased against fish that are going to be, that it's biased based upon what bait you put on there. Electrofishing has much less bias. You get a much wider range of sizes and a much wider range of species. It's easy to deploy in many different habitats, and so that's why we use it. And so we could talk a lot about electrofishing. I just want to provide some very basic details here that I think are important. So it works by causing involuntary muscle spasms in the fish. And because most fish have a swim bladder, they start to rise to the surface, and because they can't fight against that rise because their muscles are spasming, they just float to the surface and you can pick them up with a dip net. The fish recover quickly once they're removed from the electric field, and so it is a relatively non-lethal way to sample a great deal of fish. You do get some mortality under certain conditions. All right, for example, cold water. If you have longer species like a muskie or a pike, what happens is those long species have long muscles along their back, and when those muscles contract, it actually can dislodge vertebrae and can break their back. So we often, if we're fishing somewhere where we know and we see a muskie or a pike and we're not really after them, we'll step off the pedal and let them get away because we don't want to shock them too much. Excuse me. AC shocking causes more mortality than DC shocking, but AC shocking hits them harder, so you get more fish. So there's kind of a trade-off there. Either way, the mortality rates are often quite low and are often and probably better or at least the same as other gears. Realize that if you're sampling fish, you're stressing them and you're going to likely cause some mortality. That's why we make sure that we do things in an ethical manner. That's why we make sure we get as much data as we can, because we are stressing these fish out. I said that there's some bias to electrofishing. The main bias is against very small fish and very large fish. Very small fish don't absorb enough energy. They don't have a very big voltage drop across their body, so they're not as affected by the electric field. Very large fish, often when they first sense it and they have that first muscle spasm, because they're large, their muscles are very strong, and that first involuntary spasm actually propels them out of the field where they can escape. And a lot of times you'll notice very small fish swimming through the electric field and they're not even affected by it. But we're talking pretty small fish. You can still get small fish with electrofishing, and certainly different gears have different success with small fish. For example, a backpack electroshocker or an electric seine in a stream, you get many small fish. And as I said, the larger fish absorb more energy. They have a greater voltage drop, so they're affected more, except to when you get the really big ones that can be propelled out of the field. So when we talk about electrofishing, of course you can do it from a boat, you can do it from a backpack, you can do it from a seine. I've seen an electric trawl before. There's some things we have to think about as far as theory goes. The water conductivity is very important. Obviously, conductivity is how well the water conducts an electric current. if you're working with electric current, this is very important. That's why we try to measure it every chance we get. This is also influenced by temperature. Temperature and conductivity sort of work together. You got to have a measure of both. If the conductivity is too low, which means the resistance is very high, then the electricity does not flow well. So to compensate, you have to crank up the box in your electrofisher. You have to crank out more voltage to try to force your, think of a, I don't know, if you were, the difference between walking alongside a swimming pool and swimming in the swimming pool. When you're in the pool, there's more resistance, and so you have to work a lot harder to go the same distance. It's kind of the same thing. If the conductivity is low, the electrons don't want to flow, and you have to add more power to get them to flow. At the other end of the spectrum, if the current's too high, if the conductivity is too high, then the current is too high. The current flows really well. And in fact, the current will flow around the fish because the fish will have more resistance than the water it's swimming in. And so the current's always going to take the path of least resistance, which might be around the fish instead of through the fish. And so the fish is not as affected. Another problem is often you have breakers on your generator that are designed to trip when the current gets too high. And so if the flow and the current's too high, you might trip a breaker. So your solution here is to reduce the number of droppers, reduce the surface area of your electrodes. And so you put less juice into the water. You get your best electrofishing when the conductivity of the water matches the conductivity of the fish. That way they're all like one big circuit and the electricity flows right through the fish. Rule of thumb, roughly we're talking 300 to 400, maybe 450 microsiemens per centimeter conductivity. That's roughly the conductivity of a fish. And so when your water conductivity is around that, that's when you have your best electrofishing. So let's talk about electricity briefly so that we can understand what's going on here. Electricity is flowing electrons, okay? You use a spinning generator to push electrons down a wire or through the water. So it's the flow of electrons is basically how we're going to define electricity. So when those electrons are flowing, they have a certain amount of power, or excuse me, a certain amount of energy to them. All right. So if you could imagine if you were throwing electrons, how hard you throw the electrons would be the voltage. Okay. Voltage is technically a difference in potential, but it's really about how much energy each electron has. Does the electron not have a lot of energy and it's just kind of gliding along? That would be low voltage. Or does it have a tremendous amount of punch and that electron is going really hard? That would be high voltage. Another concept is current, which is measured in amps. That is how many electrons move past a point in a given time. So it's the number of electrons. And so it's both voltage and current that influence how well your electrofisher works. Voltage is measured, is symbolized by V. Current is symbolized by I. So it's how many electrons and how hard they're moving. All right. The other concept here is resistance, which is measured in ohms, and that is symbolized by the letter R. Well, this is the opposite of conductivity. Okay. So something that has high resistance has low conductivity and vice versa. And so that is, if conductivity is how well the water carries an electric current, resistance is how well it resists an electron flow. These are related by Ohm's law, which is I equals V over R, or you rearrange it, V equals IR. So the voltage and the current are related to the resistance in this way. All right, this is give you an idea of the concepts of current and voltage. Remember that current is the number of electrons flowing past a point during a point in time, where voltage is how much energy each of those electrons has. So these ping pong balls represent electrons, and so as the electrons are flowing, that's electricity. And so this is a low current. Now that was a low current because you had a few electrons flowing at a point in time. This is high current. So of course high current is a lot of electrons flowing at one time. So that's current, that's how many are flowing. Now let's talk about voltage. Voltage is how much energy each one has, or how hard you throw it. So this is low voltage. All right, that was low voltage, and also you could say low current because I didn't throw very many. This is high voltage. See the difference? Same current, I didn't throw very many electrons, but they were a lot harder. So that's the idea between voltage and current, and the relationship between those two. So for example, if you look at this I equals V divided by R, if you're out on a given lake, it has a certain conductivity, so it has a certain resistance. Resistance doesn't change. But if you increase the voltage that's coming out of your generator, then you're going to also increase the amperage. So by increasing the voltage, you can carry more electrons. So both increasing the voltage will increase the current. If you decrease the resistance, you also increase the current. Right? And so we said this. We said if you got higher conductivity, the electrons flow better. And so if you have water that has lower resistance, for the same voltage, you will have more electrons flowing through it. Now, since voltage and amperage, voltage and current are both important here, we actually want to combine them. And it's the combination of those that influences the efficiency of your electrofisher. And the combination of those is called power. Power is measured in watts. Power is volts times amps, or volts times current. Okay? So if you want to increase the power, you can increase the voltage, or you can increase the current, or you can do a little of both. So you think about it, if you have a few electrons, but they're moving, they got more energy in them, they're moving harder, that could have the same power as many electrons that don't have a lot of energy behind them. All right? That's how volts and amps are related. And if you think about power, power is a concept that you can kind of, you can imagine in your head things that are powerful or things that take more power, right? And so if you're trying to move electrons, if you put more power into them, you can move those electrons harder. They've got more punch to them. Or you can use more power to throw more electrons through the water. Either way, increasing the power can increase the volts or the amps or both. And power is, you can relate that to how much gas you burn, how big an engine you've got. If you got a bigger engine, you burn more gas, that's more power. You can move more electrons through the water and you can put more punch into those electrons. Now, if you have, here's where this comes into electrofishing, okay? Say you've got the same voltage coming out of your box, but you go to different lakes. And different lakes often have different conductivity. And so if the voltage is the same on your electroshocking boat, but you go to different lakes, you're going to have different current, right? Because one's going to have higher conductivity, and so you're going to be able to throw more electrons through the water for the same voltage. And so you're going to have more power being put in to the lake that has more higher conductivity. All right. Well, this is a problem because now you're talking about non-standard effort. We want everybody to go electrofishing with the same amount of effort. So if you go out for an hour and I go out for an hour, we're putting the same amount of effort in. But if we're in different places with different conductivities and we don't vary the voltage, we know that we're going to have different effort because you're going to have different current in these different lakes. And so we've got this idea called the power transfer theory, which is that we standardize electrofishing based upon power. So if everybody puts the same power into the water, then everybody is fishing in a standardized manner. And so the idea here is that every time you go out and electrofish, you measure the temperature and the conductivity of the water, all right? And then based upon Ohm's law, which we saw, we can adjust to put about 3,000 watts of power into the water. And so depending upon what my conductivity is, I'm going to put in so many volts. I know that based upon this conductivity and these number of volts, I'm going to get this many amps. I'm going to get this rate of flow of electrons through the water, and that's going to equal 3,000 watts, my volts times my amps. Now I go to a different lake and say this lake has higher conductivity, all right? That means I need to turn my voltage down because it's easier for the electrons to flow, so I don't need to put as much punch into each one. I turn my volts down, then my amps are also going to decrease, but I do it in such a way that the volts times the amps still equals 3,000 watts. No matter where I go, I'm trying to get 3,000 watts of power into the water. That way, I can compare my electrofishing results from this lake and that lake and my boat to your boat and so on. There's a lot more that goes into standardization, but that's the basic idea. So no matter what the water quality, no matter which generator or boat, you're always putting the same power into the water, so things are more standard. That's power transfer theory. Okay, last concept here is AC versus DC shocking. Now, both work for fish. Some states have outlawed AC shocking because you remember I told you that AC causes more mortality for the fish. And so, for example, Missouri, it's not legal to do AC shocking. Here in Kentucky, I think you can do both. All generators are AC or alternating current. So the current flows this way, then that way, then this way, then that way. The electrons go this way, then they go that way, then they go this way, then they go that way. All right. The electricity coming out of the socket in the wall is AC. The electricity that runs this computer or this light is AC. All right. All generators are AC. Okay. So you always start with AC, and you can go from that straight into the water. Or you can put that into a brain box and you can modify it and turn it into DC or direct current. Direct current is the electrons only go one way. So that's a car battery or the AA battery or any kind of battery where the current just goes in one direction. So all batteries are DC. DC has lower mortality for the fish. Another neat thing about DC is you get something called electrotaxis, which is it actually attracts the fish. And you can get fish that will involuntarily swim towards your electric probe. And this is really very useful. For example, if you think about our backpack shocker, the backpack shocker runs off a battery. It's DC. And if you're shocking in a stream with lots of small fish and lots of cover, you can put the probe near the cover and the fish will actually swim out of the cover. It's not magic. They don't just come swimming straight up and then jumping into your net. But if you get the right settings, it is pretty remarkable how those fish do swim toward one probe of the DC setup. Now, we often use pulsed DC, which it means it sends the current in one direction, but it turns it on, turns it off, turns it on, turns it off, turns it on, turns it off. So it pulses it, all right? And you can adjust the pulses per second, how often it turns it on and turns it off. You can also adjust things like duty cycle, and we can talk a lot about different ways to do electrofishing. But basically, if you want to think about pulsed DC, which is what we have for our backpack shocker, where it's turning it on and turning it off rapidly every second. By doing that, you can adjust that and actually customize your settings for certain species. So, for example, you get lower pulses per second, often attract larger fish, especially larger catfish, we know. One way we know this, it's called calling up fish. If you've ever seen one of those old school telephones where it's on the wall and they go, yeah, connecting to, whatever, they crank it up. They're cranking it up because that's a generator in there. This is, those phones came out before electricity was common, and so you would have to crank it to create some electricity, which is stored in a capacitor in there, and that powered the phone call. Well, that's a certain low pulse per second of DC current, and somebody found out that if you took that crank and stuck it in the water and turned it, big catfish started floating up, and that's why they call it calling up catfish. If you go to higher pulses per second, like 120 pulses per second, you get a lot of gizzard shad and smaller species. Usually 60 pulses per second is about the most common setting. As I said, the DC is easier on the fish, but it doesn't stun them as well. So you'll see a lot of fish when you're DC shocking that will roll and then immediately right themselves and escape. Whereas with AC, the fish roll and they're there. You can pick them up. So that's one of the trade-offs between the two. Okay, well, just some examples. This is a typical setup of a boat electrofisher. The way this is set up is the boat hull is the, I want to say the anode, I'm not quite sure, whereas these would be the cathode, or the opposite one. These are on the same circuit here. And the current flows from the generator out to these wires, and then it flows through the water back to the hull of the boat, which is also attached to the generator. And as long as you're standing on the boat, you're a bird on the wire. You're part of the circuit. The current's not going to flow through you, and so you're completely safe. Stick your hand in the water. Now the current might want to flow, instead of flowing straight back to the hull, it might flow through your hand, up your arm, across your heart, and get back to the hull. And that's bad news. But then this creates an electric field in the front of the boat where you pick up the fish. Other examples of electrofishing on a smaller scale, we've got an electric seine here. So you've got several students. Here's a generator right there. And you've got these droppers all along this seine right here. And when these two people on either end press the button, it creates a field, and then you see all the students walking behind, and they're dipping up fish as they're stunned. And in class, we did some backpack electroshocking, and you see here's another example of that too. And if I want to go back, this is the electric seine is an AC shocking, and then of course the backpack shocker is DC shocking. All right, well, we could talk a lot about electrofishing, a lot about other sampling gears, but that's all we have time for today. So I'll talk to you later. See ya.